So this is the second part of kind of the analysis of the Markov chain associated with chutes and ladders. In this part of the analysis, we're going to focus on how many turns does it take to end up on space 8 from any of the other spaces. So essentially we're viewing as ending up on space 8 as finishing this round of the game. So one thing to kind of remind ourselves is if we're interested in how many spins that it's going to take us to go from, say, space 1 to space 8, from a Markov chain perspective, we're asking ourselves, what's the expected first passage time from going from state 1 to state 8? So the state associated with space 1 to the state associated with space 8. And one thing, kind of the way we derive the expected first passage time equations was that we saw that the expected first passage time between state 1 or space 1 and space 8 relied on knowing the expected first passage time from space 3, 4, 5, 6, 7, or 3, 4, 5, 6 to space 8. So what we're going to be able to do right now, we're interested in kind of the target of getting to space 8. We're going to find the expected first passage times for all other states using this set of equations. So if we cared about a different kind of ending state or target state as opposed to space 8, we'd have to kind of derive a similar but slightly different set of equations where we're focused on getting to that other space. So let's start looking at deriving the equations. Now, let's look at, and we're going to use kind of mu. We're interested in knowing mu of 1 and 8. Basically, what mu of 1, 8 is the expected number of turns or expected number of transitions required to move from state 1 or space 1 to space 8. And the way we derived the expected first passage time equations was we looked at, well, where can we move out of space 1? And then after we make that move, we need to figure out what's the expected first passage time from kind of the intermediate state that we end up in after we move out of state 1. So we're going to look at doing a transition, and then from each possible space that transition can occur to, we're going to look at their expected first passage times. So for the expected first passage time, we know we make kind of essentially one transition, so we always kind of have a 1 to start the expected first passage time equations. Remember, in our derivation, that came from the fact that all the probability transitions out of space 1 were included in our analysis. So we now look, and the one thing is, since we're focusing on where do we transition out of space 1 or state 1, we can look at space 1's or state 1's transition probability row in the transition probability matrix. So what we're going to look at is from space 1, we have a 25% chance of transitioning to space 3. And then once we transition to space 3, we have to go from space 3 to space 8. So we're interested in basically the expected number of steps required to go from 3 to 8. And then we'll also have for space 4, we have a 25% chance of transitioning from 1 to 8. And then if we end up in space 4, the expected number of steps to go from 4 to 8, so essentially complete reaching our target, is mu of 4, 8. And then we can also reach space 5, or transition to space 5 from space 1, so we have a 0.5 mu of 5, 8. And we're going to have equations for each space, except for each possible space / state, looking at the first passage times. So we'll also have mu of 3, 8, and we're going to look at all the transitions out of space 3 that don't involve ending up in space 8. So this one that we've kind of incorporated in is that if we end up transitioning to space 8, we don't need to go anywhere further. So essentially, to a certain extent, we can interpret once we're in space 8, its kind of first passage time into space 8 is defined as 0. So look at mu of 3 comma 8, look at space 3's row, so we end up with a 0.5 mu of 4 comma 8 plus a 0.25 of mu of 5 comma 8 plus a 0.25 of a mu of 6 comma 8. For mu of 4 comma 8, again, we start with 1, and then we look at space 4's transition probability row, the row associated with the transition probability. So I have a 0.25 mu of 4 comma 8, because there's a 25% chance we end up back in space 4. We have a 0.25 probability associated with mu of 5 comma 8 plus a 0.25 probability of mu of 6 comma 8. Now again, we don't include 0.25 times mu of 8 comma 8, because once we transition to space 8, we kind of have identified that we're already there. So we'll also have a mu of 5 comma 8. Mu of 5 comma 8 is 1 plus 0.25 mu of 4 comma 8 plus 0.25 of mu of 5 comma 8 plus 0.25 of mu of 6 comma 8. And again, we ignore kind of the target space in our derivation of the expected first passage time constraints. So then for mu of 6 comma 8, we had a 1 plus 0.25 mu of 4 comma 8 plus 0.5 mu of 6 comma 8. So what we're going to look for is we're going to look for the solution to these equations. We're going to we'll set up kind of a solver area, and we're looking for mu of 1 comma 8, mu of 3 comma 8, mu of 4 comma 8, mu of 5 comma 8, and then mu of 6 comma 8. And then we'll look at kind of the left-hand side of our equations and the right-hand side. And again, this is just kind of my preference. I like to bring all the variables over to the left-hand side. So looking at for this first equation, looking at the leading coefficients, we'll have a 1 for mu of 8. We'll have a minus 0.25 for mu of 3 of 8. Again, we're just bringing over all of the variables to the left-hand side. We'll have a minus 0.25 for mu of 4 comma 8, and then minus 0.5 for 5 comma 8. And then all the left-hand sides, we'll end up calculating them. All the right-hand sides of these will be ones. So for our second, when we're dealing with mu 3 comma 8, we'll have a 0 for mu 1 8, I have a 1 for 3 8, 4 8, we'll have a 0.5, 5 8, we'll have a 0.25. Actually, it should be negative 0.5 because we're bringing them over the left-hand side. We'll have a negative 0.25 and a negative 0.25 for mu of 6 comma 8. So again, all we're doing is we're looking at the entries associated with each of these mu's, taking the negatives because we're subtracting them over. So for when we look at mu 4 comma 8, we'll subtract 0.25 from the existing 1 over there. So for deriving these, we'll have a 0 for 1 8, 0 for 3 8, a 0.75 for mu of 4 8, a minus 0.25 for mu of 5 comma 8, and minus 0.25 for 6 comma 8 when we're looking at the mu of 4 comma 8 equation. So for mu of 5 comma 8, we'll have a 0, a minus 0.25, a 0.75 for mu 5 comma 8, and a minus 0.25 for mu of 6 comma 8. And then for mu 6 comma 8, we'll have a 0, a minus 0.25, a 0, and then we'll have a 0.5 because we have a 1 already over there. We're subtracting off minus 0.58. So we can look at the mu values that we're looking to calculate, and these are kind of going to be where our decisions are. So we're going to look at taking the sum product of each row or each equation with the mu values, and then we'll put in the dollar signs to be able to copy and paste down. And then we can bring up our solver. So we can choose any mathematical expression. It doesn't matter if we're maxing or minning because there's going to be a unique solution. We're changing the mu values, and then we want the left-hand sides equal to the right-hand sides. And then just get the simplex, just make sure it's nice and kind of solve. Okay, so what we're looking at here is we kind of say that, roughly speaking, if we are on 1, it's going to take us about 5 turns to reach state 8. From 3, it's going to take us about 5 turns to reach state 8. Then for 4, 5, and 6, it's going to take us about 4 turns. And that somewhat, kind of intuitively, that kind of makes sense, is that if I'm on 4, 5, or 6, I have a 25% chance to end up rolling and spinning and ending up on 8. And basically, if I start at 4, if I'm on space 4, I'm going to basically transition once I reach space 4, 5, or 6, I'm basically just transitioning between those until I spin and reach space 8. Now, one other kind of interesting thing with the structure of this Markov chain is that once we reach space 8, we take one step and reach space 1. So if one thing that we can look at is, instead of the expected first passage times, what's the expected recurrence time of space 8? So once I am in space 8, how many turns before I reach space 8 again? Now, we had solved, and remember, if I wanted to know kind of mu of 8, 8, that is equal to 1 divided by pi of space 8. So if I'm on average in space 8 X percentage of the time, then this expression gives me, well, the expected number of turns before I'm in space 8 again. And we had solved for that. We had seen that pi of 8 was 0.16 when we solved for the steady state equations in the other video. So if we look at what 1 over 0.16 is, it's 6.25. So what that means is that once I reach space 8, in roughly 6.25 turns, I'll be back in space 8. And that makes a lot of sense. That kind of fits with what we examined for our expected first passage time from space 1 to space 8. Because you remember, if we're in space 8, our next turn automatically brings us to space 1. And that's where, so once we get to space 1, on average, we have 5.25 turns before we reach space 8 again. So this kind of difference, is 1%, or this one step difference, makes a lot of sense, or makes intuitive sense given the structure of the Markov chain. So that's all kind of for this this analysis of the Markov chain with the chutes and ladders. Okay.